Hi, I'm Ben-Yaakov. This presentation is entitled Advances in Modeling Class 2 Ceramic Capacitor Loss under High Current and High Voltage. We have now two types of ceramic capacitors. We have the power electric capacitors and the ferroelectric capacitor. These are the materials. Now the power electric, like the C0G or NPO, are characterized by a low ESR, a small relative dielectric constant, and therefore they are larger in size, and therefore they are limited to about 0.2 microfarad. There are some larger than that, but there is some limitation there. On the other hand, the ferroelectric capacitors, or material I should say, like the X7R, they have a much larger relative dielectric constant, and consequently they are much smaller in size for the same capacitance, and you can get them at a much larger capacitance therefore, but they have a somewhat higher ESR than the power electric capacitor. In this presentation I'm going to concentrate on the class 2 and the ferroelectric capacitors primarily, and in particular to talk about the losses due to high current. In a typical datasheet of capacitor, this is for say X7R, we find the dependence of the capacitance on the bias voltage, the temperature characteristics, but we are concerned here with the question of losses, so we have also here the ESR. Okay, this is the resistance, the series resistance of the capacitor, and this will be of course of importance when we are talking about a stage like a buck converter. We have a ripple here which will be passing through the capacitor and eventually can cause high rise of temperature. Of course, in other applications like resonant converter, the ripple current, or the current, the AC current, is much higher. So there is a question, what are the losses and what will be the temperature rise of such capacitor. In the data sheet we also find plots like these, and these are currents. Here this is current and this is temperature rise, although it's not always defined what is the terminal resistance of the fixture that is holding the capacitor, but we get this information which says that, say, for a given current, these are for different frequencies, for a given frequency, a given current, you'll have this temperature rise. As it turns out, these curves are based on this ESR. This is at least from what I've seen. So that basically they are based on the assumption that at high current the losses are like in the small signal measurement that were made for getting this curve. This is a small signal curve, that is, it was obtained by a small signal, and then it is sort of carried out to higher current, and the question is if this is correct. So the subject matter of this presentation is what are the losses of the ceramic capacitor at high current. There is another issue, which is how is this loss dependent on the bias voltage. This is also something which is not very clear. In fact, there are some conflicting data on this part. I'm not going to go into it. Now, when it comes to ferromagnetic losses, ferrite losses, we are usually using the Steinmetz equation, which is basically a template. Okay, so this is the template, and it is a function. The losses are assumed to be a function of the frequency, and B is actually the peak magnetic flux density, and here there are some parameters A and B which are sort of fitted for each material. Like if there is some material like a 3F3 for example, or Ferrix cube, what the vendor is doing, or the manufacturer, is actually testing it and fitting the results of the losses to this equation, and by this extracting these constants. So this is very well known in the literature and widely used by engineers, of course. There is an improvement to the Steinmetz equation, the so-called generalized Steinmetz equation. Actually, there's an improved generalized Steinmetz equation, the IGSE, which has a different form a little bit. It has here the derivative of the magnetic flux density, and it was shown that this template fits better the cases in which the excitation is not sinusoidal. In the basic Steinmetz equation, here the fitting is best for sinusoidal waveform, while here it is extended to non-sinusoidal waveform. And the nice thing about it is that the coefficient, the parameters, alpha and beta, or A and B, are the same as in the small signal. So you can run a small signal testing and then use it for the larger signal. So what about the dielectric losses that we have in capacitors? Now, as it turns out, Steinmetz, and here's a picture of him, already sort of predicted that the losses will be of this form. This was based on observation and some analytical consideration. He didn't do any testing about it. And what he said is that the losses are expected to be a function of the frequency and the displacement to which the dielectric material is exposed to. Now, template, of course, is very similar to what we are using in the ferromagnetic case, okay? Although we are talking here about displacement and not magnetic flux density, but the form is really very similar. Now, what is a displacement? The definition is the total dielectric constant times the electric field, which is the voltage divided by the distance between the plates, and then it comes out to be the charge density. That is the charge divided by the area of the electrode. Now, in a 2018 paper, I've pointed out to the fact that you can represent the losses as a parallel resistor rather than a series resistor. In fact, this will be more correct because the electric losses are a function of the voltage, not of the current. So this is more natural to the physical behavior of the dielectric material, which is exposed to a voltage, and therefore there are some losses. And what I've found is that the behavior of the ESR as a function of frequency fits very well with this function, like some k over frequency. It's 1 over frequency, okay? So that you can describe this ESR, this is again the low signal ESR, you can describe it as some constant over frequency plus some saturation level, which is this level here, okay? And then using this, when you plot this approximation and you put it on top of the actual curve, you find that there is a one-to-one relationship. There's an excellent fitting between these two. So you can take now this relationship and work it out into what will be the expression for the power loss. And lo and behold, what we are getting is that we are getting something of this nature. This will be the expression for the power loss based on this model here. And as you can see, it very well fits with the Steinmetz prediction and with the ferromagnetic template that we are using in the case of ferrite material. Following this, Professor Kolar and his group, including Dr. Menzi, published a paper which sort of expand this idea even farther. They have shown that if you use a template like this, which is again very similar to the Steinmetz template, but here we have the peak charge of the capacitor that it's reaching every cycle, using again alpha and beta as parameters. They have shown that this template fits very well with measured losses, so you can actually extract from measurement these constant to describe the losses of the capacitor, but in this case at high current level or relatively high current levels. And here are some of the results. This is the template. For this particular material, it was found that the alpha is 1 and the beta is 2.12. And what we see here are the experimental dots. Here are the dots are the experimental results. The broken line is the fitting by this equation. And since this is to the power here, when you plot it in a log-log scale, you have straight line. Again, this is power as a function of the peak charge of the capacitor. And this is, of course, very, very similar to what we have or what we use in the case of the ferromagnetic material. We have these curves very similarly, only that in the case of the ferromagnetic material, we are using here the magnetic flux density rather than the Q. But the charge, or the peak charge, is really not a very convenient measure or unit to work with, not an engineering value, because we are working with current, and of course it can be translated, it can be measured, but it will be much more convenient to have the power related to the current rather than the charge. And this was done in a work that is described in a paper to be published just now, in which I've taken part. And in this case, we have moved from the charge to the current. This can be done, of course, because the current is the derivative of the charge. So when you take this into account, and then you take the basic template with the charge and replace it with the current, you get this equation, which again is very similar to the classical Steinmetz template. Alpha and beta will be those of the basic template, of the basic expression here. Only in this case, the losses are a function of the RMS current. So here it is again. The current is related to the charge. This is the expression for the ESR. This is now the losses as a function of the current, from which you can then, combining again the ESR expression here and this expression here, you can get a definition of the ESR as a function of the current. So this is actually what we want. We want to know what is the ESR, so that, which is a function of the current, as we can understand here. And then by knowing the coefficient here, or the parameters, the K, alpha and beta of the fitting, then we can find what will be the losses by the basic equation of ESR times I squared. And here are some experimental results. Again, the dots are the experimental measured points. The broken line is the curve according to the model that was fitted to the measurements. We have here different frequencies. This is the excitation, which was a voltage, AC voltage. This is the current. And here is the power dissipated for each one of the excitation, which correspond to a given current. Now, using this information and the model, we can see that there is a very good match, and this will be for the low current or the small signal information given by the vendor. This is the information given by the vendor. It's not given for the particular size, the capacitance that has been tested, 0.47, so I've sort of interpolated. These are the model prediction, and the straight line is actually a sort of a interpolated line. As we can see, there is a very good fitting, and this would be for the low current. Now for the high current, we can then use the model and plug it into a simulation program, which I've done. And what we see here is how the ESR is expected to increase with the current. This voltage is actually representing current. It's the way the simulation was done. It's a behavioral simulation. So it is coded into voltage, but this will be like 100 milliamp. So we see that the ESR is in fact going up. This is again ohms here. So it's going from, say, 8 ohms to 20, 21, depending on the current. And also we can see here the dependence on the frequency. We see that as the frequency goes up, the ESR, this is now the ESR, is going down. And we see here also the dependence of the ESR on the current. This is, however, a logarithmic scale, therefore we don't see it that much as we see it here. This is a linear scale, and this is the logarithmic. Now the models that I've just shown are what we called device-oriented models. That is, these are models that the template has to be fitted to each capacitor, because the size of the capacitor will determine also the coefficient of the parameters of the Steinitz equation. We would like to have, of course, a material-oriented model like we have in the ferrite case. In the ferrite case, we have, on the one hand, the Steinitz equation for the loss of the material, and then we have some information about the structure of the core, and when we combine the two, we can calculate the loss. And in this paper, which is also about to be published, there is one step toward accomplishing this desired situation in which the model will be based on the material rather than individually on each unit. So here's the idea. If we look at the multi-layer ceramic capacitor, which is used of course for large capacitances, what we see is some area here. These are the electrodes. We assume that all of them are the same, the area is the same. Then we see the interleaved electrodes, okay, like comb here. These are the electrodes. And then we have the material itself, the dielectric material in between. And the total of which gives us the capacitance. So the total capacitance will be the dielectric constant times the total area divided by the distance between the electrode, and let's assume that the distance is the same for all layers. Okay, so the area now, of course, is the total area. So if we have n sections, then it will be n times a divided by t. So we have here actually two parts. One is the material specific. This is dielectric constant, which is typical for each material, and of course it's non-linear, etc., temperature dependent, very much like in the case of the ferromagnetic case. This is like the permeability of the material in the ferromagnetic case. And then we have a section here which is related to the construction. And again, it is like in the case of the ferromagnetic case, in which we have on the one hand losses per material, and then of course the total loss depends on the volume of the unit. To investigate this, data was obtained from Knowles, a manufacturer of ceramic capacitor, and here we have two sets or two groups of capacitors. These are capacitors, okay, these are the sizes, etc. And here we have the X7R group, okay, and then we have the other group, Highteka, which is a proprietary material of Knowles. So we have two groups here. And for this particular capacitor, we got with these values, this is the breakdown voltage and the capacitance, we got the thickness of between the electrodes, the area of the electrodes, and the volume enclosed within each section, which is very important. We'll talk about it in a minute. Okay, so this was done. And now we have here the coefficient for the Steinitz template based on the charge, Q peak. Okay, this is the earlier model. Now, starting with the basic template here, which is based on Q, we can translate it to the displacement parameters by these relationships, that the displacement is Q over A, as I said before. There is some constant here depending on the number of layers and size, etc. And then we go on and we find that this expression boils down to this one, and eventually absorbing this added constant into the original constant, we get this expression, which is very similar to this expression, except that now we have this displacement, which is material oriented. Now this is for the basic Steinitz equation, and this is for the improved template for the non-sinusoidal waveform. And here now the K here this new K, is now a function of the original K, original constant, plus structural relationship, which is the area of the electrode as well as the volume enclosed between the electrode. So this is again very similar to what we have now in the ferromagnetic case. We have on the one hand losses which are dependent on the material, and then we need some information about the structure of the device. In the case of the core, we need the length, the magnetic pattern, etc., in order to do all the final calculation. And the same thing goes here. We need this information. This information is not available now. And hopefully, if this idea of a material-oriented model will be accepted, then vendors can actually provide this information, which they do have available. I mean, it's not as if they have to do something special about it. This is information that is the structure of the unit and this area and this volume. And by this, we'll be able to model a family of capacitor rather than the individual capacitor. And here are some of the results. These are experimental results. And I think it's very impressive to see that when you have the model based on the charge, you have for each capacitor a different line, because each capacitor has its own model, its own parameters. On the other hand, if you are using the material-oriented model, each material has its own line, and this will be for one material, and this is for another. As you remember, we have here two groups, so we have here just two lines, which means that we have the same model, which is now describing a group, a family of capacitor, rather than the individual capacitor, like in this case. So let me just summarize what we have seen. First of all, I think there are some significant advances in the modeling of ceramic capacitor losses. We still miss high frequency information. Most of the information gathered in the paper that I've shown are for relatively low frequency because it was intended for filters rather than for converters. So there is some need for information of high frequency. And the point actually that I've shown is that we are now moving from the device-oriented model to a material model in which we need material information and structural information, the area of the electrode and the volume closed in each one of the chambers. And this is, of course, very similar to what we have in the ferromagnetic case, in which we have the Steinitz equation on one side, and then we have the structure of the core on the other side, and combining the two, we can estimate the total loss that we'll have in a inductor or a transformer. So this brings me to the end of this presentation. I hope you found it of interest. Thank you very much.